will show up in a second. Okay. Perfect. So let's see. That's correct. Okay, great. Okay, I think let's begin. So Angela is here. Yeah. Oh, sorry. Let me start again. So thank you and welcome everybody back to the online SPICE-SPIN+ seminars. Sorry. Oh, okay. I'm making mistakes. Sorry. Here organized by the Spin Film Interdisciplinary Center that I lead together with Angela Wittmann and Karina University, and in collaboration with the SPIN+X Collaborative Research Center led by Martin Schliemann and Booker Hillebrands in Kaiserslautern, Matthias Chloe in Mainz. This is a Zoom webinar format, so please write your Q&A, your questions in the Q&A or in the chat, and then I will pass you or promote you to panelists who ask directly the speaker afterwards. Please keep in mind that we have some workshops ongoing, that we will not have the seminar during the ongoing workshops. Like next week, there will not be a seminar, but at the end of the month, there will be another one. And then a few more on the scattered ones in July, and then we have a break in August until the middle of September. Today is a pleasure to welcome Luqiao Liu. He's a professor, electrical engineer at MIT, had his bachelor's in Peking University, and in 2012 in applied physics from Cornell University. Works on spintronic materials and integrated memories, device memories and logics and communications in the application focus areas, and has had many awards, of course, Macmillan Award for NSF Career Award, an Air Force Young Investigation Award, and the Sloan Fellowships, as well as the International Union of Pure and Applied Physics for Young Scientists Awards. So with this, I'm going to stop sharing and ask you, please, Luqiao, to start, and I will mute myself here and on the video to give you more bandwidth, and we're looking forward to your talk. Thank you.
Hi, good afternoon, everyone. Yeah, thank you, Professor Sino, for giving the nice introduction, and thank you for giving me the opportunity to speak here. So today I'm going to talk about our recent study, both experimentally and theoretically, about magnon-magnon interaction, particularly utilizing the dipolar interaction between magnons in order to realize non-reciprocal transport of magnons, as well as some topological band structures. So since here I'm going to talk about non-reciprocal transport, so maybe I can talk a little bit about the application of magnetic devices, magnetic components, as a non-reciprocal component inside circuit. So we know actually magnetic materials, of course, have been widely studied as memory. But besides memory of information storage, another important usage of magnetic material is to utilize its non-reciprocity. So a classical example is this kind of radar. So for example, if you want to transmit and receive signals using radar, you have an antenna. So basically the transmitter, the signal source, and the detector, actually they are connected to the same antenna. But in order to separate the forward and backward signals apart, actually you need to utilize such an isolator so that the signals only go from the source to the antenna, and then the reflected RF or microwave signals detected from antenna only goes to the detector, but not back to the signal source. So this is a quite classical application of isolation devices. And then these days, actually, people see more and more demand from quantum computing. For example, this is a classical, very standard quantum computing circuit. So you have your qubit or your quantum circuit as a dilution fridge at a very low temperature. And then you have some control circuit, control signals coming in from the left circuit, and then you have your detector on the right side, right branch of this circuit. So along the way out, actually you will notice that there are usually installed a few isolators so that signals from the qubit only goes out, from the quantum circuit only goes out to the detector, but any external noise sources like the radiation from the room temperature actually does not go back to the dilution fridge. So this is just to protect the sensitive quantum state of the circuit there. So actually, to give you a more intuitive picture, so actually this is a typical isolator device. So this is inside the dilution fridge. You can see that at the very low temperature stage, usually you need to install one or maybe even more circuit boxes like this, and each of them is about a few centimeters in diameter, in literal size. And then it can have 2 or 3 ports, which is used as a circulator or isolator. If you open it up, you will see that the internal structure looks like this. So the central part is a ferrite core, iron core, in the middle. So then how it works is like this. So you have a input signal, input microwave or few gigahertz signal coming in, and then you can decompose it into 2 orthogonal modes, and those 2 orthogonal modes have opposite polarity, circular polarization. So one of them goes clockwise, and the other one goes counterclockwise. So along this this cylinder, so actually you will have destructive or constructive interference between those 2 modes, depending on your location. Because of the magnetic permeability, magnetic susceptibility of this iron core, so for those two modes with opposite handedness, they have slightly different magnetic susceptibility. Therefore, for one location, for one port, for example, port 2, it corresponds to a constructive interference between those 2 waves, and then for the other port, which is port 3, it corresponds to a destructive interference between those 2. Therefore, then you can get one out. The signal only go from port 1 to port 2, but not go to port 3. So this is how you can isolate signals. And then when it comes back, it only goes from port 2 to port 3, but not go back to port 1. So in general, this is based upon the Faraday effect. It's very similar to the Faraday effect in the optical domain, but this just happens in the microwave domain. So it utilizes the difference in the magnetic susceptibility of 2 opposite modes. So it usually works in a region very far away from magnetic resonance. Therefore, the difference in the magnetic susceptibility is usually very tiny. So you need a very large volume, a lot of magnetic material in order to realize this. So that means those devices are usually very big. As you can imagine, there is a natural demand try to minimize those kind of devices to make on-chip, fully integrated isolator circulators. So in order to realize that, actually the spin wave is probably one possible candidate. The reason is that we do know that spin wave can exhibit unidirectional transport under certain circumstances. The reason is, first of all, for spin wave, you must have some magnetic material. And magnetic material, of course, break time reversal symmetry. And that's what you need in order to isolate signals. But of course, spin wave does not always give you non-reciprocity. You still need to satisfy certain conditions in order to exhibit non-reciprocity. One of the well-known mechanisms that can lead to non-reciprocity is this kind of DMI, electricity-Maria interaction. For DMI, for example, here I chose to use the example of interfacial DMI coming from a bilayer system, and then the bottom is a heavy metal, for example, platinum, and then the top is a permalloy, nickel iron alloy. And we know at the interface, because of the exchange interaction mediated by platinum, this thin film exhibits DMI. The DMI Hamiltonian can be written in this format, and here D is just the DMI vector, and SI, SJ are 2 neighboring spins inside the magnetic layer. So now imagine if you have a spin wave propagation, propagating either from left to right or right to left, then the left spin and the right spin will have certain phase correlation. So depending on the wave vector direction, the left one is either in advance compared with the right one, or in delay compared with the right one in terms of its phase. So therefore, Si cross Sj will have opposite signs depending on the wave propagation direction. And now you can see that for different k, for different wave vector, you will gain different DMI energy. So this will exhibit itself as a asymmetry between positive and negative wave vector. So for example, if you look at this red curve, and those 2 points are having same absolute value of wave vector, but opposite direction, and then they have different frequencies. So of course, this asymmetry can be toggled, can be switched by reversing the magnetic moment orientation, or by flipping the external field direction. So for example, that's the reason why the blue line and the red line show opposite asymmetries. So of course, this kind of DMI-induced frequency shift actually can be detected, can be probed using, for example, BLS, brilliant light scattering. So for example, this is a typical experimental data you can get, which shows as a frequency shift between the 2 oppositely propagating spin waves. Okay, so this is one mechanism that can give rise to non-reciprocal spin wave transport. Another mechanism is actually even more familiar to us, which is coming from the dipolar interaction. So actually, this has been studied for maybe half a century. So basically, it's known that the magnetostatic wave, particularly the surface mode, can give rise to some non-reciprocity. So the magnetostatic surface wave is configured in this way. So you have magnetic moment, its orientation, the equilibrium magnetic moment orientation is perpendicular to your wave vector direction. So under such kind of situation, you will see that the left propagating spin wave and right propagating spin wave will actually get geometrically separated. So for example, on the top surface is mostly dominated by the right propagating spin wave, and on the bottom surface is mostly dominated by the left propagating spin wave. So as you increase the thickness of this magnetic material, then the separation of the 2 oppositely propagating spin wave will get farther and farther. So you will get almost kind of purely unidirectional transmission of spin wave on the top and the bottom surface. So this is basically the how you can get the unidirectional transport of magnetostatic surface wave. So actually, experimentally, you can selectively excite spin wave along one fixed direction, for example, by depositing antenna on, for example, on the top surface. So now, because geometrically it's closer to the top surface of this magnetic material, so it will excite the right propagating spin wave more than the left propagating spin wave. Of course, again, if you flip the equilibrium magnetic moment orientation, you will also get opposite dominant spin waves. So this is actually shown in this quantitative study where they calculated where they measure the right propagating and the left propagating spin wave magnitude. So as you can see that as you increase the thickness of this magnetic thin film, actually the top and bottom surface get further and further away from each other, and then you will get a larger asymmetry between the 2 oppositely propagating spin waves. Actually, the dipolar interaction is quite universal. So it's one of the most fundamental properties of magnetic material of spin wave. You can imagine if we can make a more efficient version of those kind of non-reciprocal transport of spin wave, it will be hopefully allow us to get useful devices. So actually, my today's talk is mostly focused on this kind of dipolar interaction induced non-reciprocal and topological band structures. So basically, I will first talk about a bilayer magnetic heterostructure. By utilizing the chiral dipolar interaction, we can realize non-reciprocal diffusions. So different from what I have been describing before, which is a single frequency coherent magnon excitation. Here I'm going to talk about non-diffusive incoherent magnon reciprocal transmission. So in the second part, I'm going to talk about how we can construct topological magnetic insulator or topological magnetic system, which has between two magnetic thin films. So here, instead of directly talking about spin waves, so here I want to draw your attention to such kind of phenomenon, which you might have noticed before, which is how dilution fridge works. So I guess many of you, hopefully everyone of you, have played with this, a fridge magnet for at least once. So basically, the fridge magnet actually has a interesting feature. So it only attaches onto the fridge with one side. If you try to flip it and then attach the fridge magnet using the picture side, actually it doesn't work. Why is this? Actually, this is not because you have extra thickness for the picture on the other side, but because of the domain configuration inside your dilution fridge. So actually, if you microscopically look at the dilution fridge magnetic domains, they look like this. So they are arranged in a certain order. So the reason that they are ordered in that way is because now if you want to ensure the magnetic flux lines to form a closed loop, you will see that they will only emerge, the residue, the street field will only emerge on the top side of this dilution fridge, but not on the bottom side. So that's the reason why it only attaches, for example, at the magnet side, because there is no dipolar field on the other side. So this is how a how a fridge magnet works. But now the question is, how is this related to a propagating spin wave? Actually, the idea is very similar. So now if you consider a propagating spin wave, but at a certain point, you let it freeze and then just take a snapshot. So now you can imagine at different regions of this magnetic thin film, it will have a magnetic moment pointing along different directions, which is very similar to the domain structures shown on the left. Now again, if you want to enforce that it is form a closed loop for the magnetic flux lines, then you will see that the street fields, dipolar field, only show up on the one side. In this case, when the spin wave points to the right, propagates to the right, it only shows up on the top surface. Now, if you want to reverse the spin wave propagation direction, you will find that actually now the street field emerges from the bottom side, but top side, there is no net street field. So actually, this is a very interesting phenomenon. I was quite surprised to learn about this in the first place. But as you can imagine, since it comes from magnetic dipolar interaction, so this should have been known for many, many years ago, because if you know Maxwell equation, you should know, in principle, you should be able to say this. But I think most recently, people get interested in this topic again. For example, in this PRL paper by Garrett Bauer, they basically emphasize on this effect. Basically, this is showing as a chirality of the dipolar field generated from propagating spin waves. In short, the dipolar field generated from traveling waves are single-sided and circular polarized. So on which side it shows up and what kind of circular polarization it has depends on the wave vector direction. So that's the reason why we call there is a chiral dipolar field. Okay, so but now you have dipolar field showing up on opposite sides of this same field, depending on your wave vector direction, but still that doesn't give you a non-reciprocity. The reason is you still have some symmetry. So the top versus bottom surface does not give you any net result. If you want to get some finite effect, you have to, for example, have two magnetic layers together. Now, if you couple two different magnetic films, actually now you break another symmetry, not only the time invertible symmetry, but also some inversion symmetry along the z-axis. So now you can actually get a non-reciprocal effect. So as I just mentioned, because, for example, if you consider the dipolar field generated from spin wave in the bottom layer, it will show up on the top surface. Now, if you consider dipolar field generated from the top layer, actually, if its equilibrium magnetic moment orientation is opposite to the bottom one, its dipolar field will show up on its bottom surface. So now, each of those two layers will sit inside the dipolar field region generated by the other. Therefore, those two are coupled together. But now, if you reverse the wave vector direction, so now you can imagine for the bottom layer, its dipolar field actually is located on the bottom region, and for the top layer, its dipolar field is generated above it. Therefore, those two layers are not sitting in each other's dipolar field region. Therefore, those two are not coupled with each other. So now you will have a non-reciprocal condition in the sense that for the right propagating spin wave, the two layers are coupled together. And then for the left propagating spin wave, the two layers are not coupled, are uncoupled. So you will get asymmetric coupling through this kind of chiral dipolar interaction. Okay, so this is a rough idea how you can utilize the dipolar interaction between two magnetic layers to realize some non-reciprocal condition. So actually, this kind of effect have been recently experimentally exploited in a few works. This work is coming from Beihang University in China. So basically, there they show that if you couple two films, the bottom one is extended film EEG, and then on top of EEG, you have some nanowire made from cobalt. So now you consider if you excite the spin wave on one side and then detect it on the other side using a complementary guide antenna, you will get this kind of non-reciprocity in the sense that when the cobalt wire is parallel with the EEG magnetic moment orientation, it allows the spin wave to go from left to right, excite spin wave, right propagating spin waves. But now if you keep some anti-parallel, so it only excites spin waves that is propagating to the left. So this is studied using this kind of spin wave propagation spectroscopy. So from this vector network analyzer transmission coefficient measurement, you can see that S21, S12 are opposite, are not the same with each other. And then this non-reciprocity can also be toggled by the external field or by the cobalt, by controlling the cobalt orientation. But of course, here is not two extended thin films, but instead cobalt here is treated as a dirt function. So it's mathematically it's treated a little bit differently from what I just described here, but the overall idea is the same. So this is an example through this kind of cobalt EEG bilayer system. And another example is this kind of permalloy ruthenium cobalt boron synthetic antiferromagnetic structure. So in this kind of synthetic antiferromagnetic structure, if you excite the spin wave, for example, in the middle, and then utilize brilliant light scattering to detect the two oppositely propagating spin waves, you will find that actually their dispersion relationship is asymmetric. So again, this is because of the dipolar interaction between the magnons of those two layers, which add external energy for the magnons. So therefore, it will either increase or decrease the magnon frequencies. So this induces this frequency asymmetry. So both of those two experiments are studied in the coherent spin wave regime, where you excite the magnons using a single frequency microwave input. So actually, we try to study this kind of phenomenon in an opposite regime, that is in the diffusive regime. So we try to see if we can still observe such kind of reciprocity if we excite a broadband, thermally populated magnons. So basically, this is an experimental geometry. So I will explain this a little bit more in the next slide. Basically, this is known as kind of non-local spin wave measurement geometry. So you have two platinum electrodes, and the left one can inject spin current, and the right one can detect spin current. And in the middle, we have a permalloy nickel iron alloy deposited on top of a EEG film, which acts as a gate. So we would like to say, due to the interaction between this nickel iron alloy and then this EEG film, because of magnon-magnon interaction, whether there will be any modulation effect played by this magnetic gate. Of course, if we want to probe the oppositely propagating spin waves, we can simply flip swap the role of the injector and detector. So, for example, inject from the right side versus inject from the left side, and then you will get the able to probe the properties of magnons along two opposite directions. So here, this is how this technique, this kind of non-local charge transfer measurement was first developed. So in this paper by Van Wee's group, basically they first showed this possibility about using the spin Hall effect on one side of the magnetic insulator to inject magnon, to excite magnon, inject spins, and then let the spins diffuse along this magnetic insulator thin film, and then on the other side, utilizing another platinum electrode to convert those spin current back into charge voltage using the inverse spin Hall effect. So between those two electrodes, the signal actually gets transmitted through the diffusion of magnons. So this is known as this kind of non-local voltage measurement. So experimentally, if you want to measure the signal, it looks like this. Usually you want to rotate the magnetic field within the film plane so that you have some modulation on the equilibrium magnetic moment orientation of the Eeg field. So actually there will be some sinusoidal signal depending on whether your magnetic moment inside Eeg is collinear or orthogonal to the injected spin. So since it comes from the diffusive transport of magnons, so you will get this kind of exponential decay, and the characteristic length is gives you the spin diffusion length. So recently, this kind of non-local charge transport measurement has been extended not only to study the magnon transport inside ferromagnet or ferrimagnetic insulator like Eeg, but also to anti-ferromagnetic insulator, for example, as done by Professor Cowie's group, as well as my own study shows. Okay, so this is basically geometry, but in this kind of original version of this kind of measurement, you can see that there is no middle gate, so it's just a simple single layer of ferrimagnetic insulator. So now we would like to add this additional magnetic metal gate, nickel iron, and see how things happen. But first of all, we want to get a baseline that is without this gate material, without this nickel iron gate. We can see that we reproduce this kind of sinusoidal behavior very well, just like the previous papers show. So this kind of sinusoidal signal. Okay, so now let's see what happens if we put additional magnetic layer, nickel iron. Well, after we have this nickel iron gate, and as we rotate the magnetic field within this film plane, we found that actually, first of all, we found that there are some sharp switching behaviors around certain angles. And those are very different from the smooth sinusoidal signals as observed before. Another important feature is that besides those kind of sharp switchings, you can also see that this non-local voltage we obtained by measuring in those two opposite configurations, that is by measuring the right propagating spin wave versus left propagating magnons, they are no longer overlapping with each other. So for example, on the case where there is no gate, you can see the red curve and the black curve, they overlap with each other. So by the way, here the red represent when we excite from the right and detect from left. The black represent the case when we excite from the left and detect on the right. You can see that they overlap with each other quite well in the case there is a single Eeg film. But when there is a bilayer of nickel iron and Eeg, you can see that this black and red curve is no longer overlapping with each other. So this means if you choose a specific field configuration and stay there, then the right propagating, the transmission efficiency for right propagating magnons is different from the transmission efficiency for left propagating magnons. So therefore, we see this kind of non-reciprocal transport behavior that is coming from the magnons. Okay, so let's do some control experiment to see where this non-reciprocity coming from, whether it comes from some nearest neighbor interaction, for example, exchange interaction between the nickel iron and Eeg film, or it comes from some a long-range interaction. For example, dipolar interaction is a long-range interaction. So which is the case here? In order to answer that question, so basically we insert some spacer layer between the nickel iron layer and then the EG film. So for example, we can choose to insert a magnesium oxide in between, or choose to insert a copper spacer in between. We found that no matter which one you insert, actually the non-reciprocity, the discrepancy between the red and the black curve still exists. Well, this suggests that this is not coming from the direct interfacial effect. No matter whether it's a standard exchange or maybe the asymmetric or the DMI interaction, so they should not be the dominating contributor to this effect. And also spin current here, since magnesium oxide should block the spin current diffusion, so it should also not be the main source for the observed phenomenon. At the same time, actually, we also replace the middle nickel iron electrode with a platinum electrode. We found that actually, if we replace nickel iron with platinum, then the overlap between the two oppositely propagating signals still overlap with each other. So all of those control experiments suggest that it's some long-range interaction instead of short-range interaction plays a dominant role. Again, here, dipolar interaction is a well-known long-range interaction. So that's consistent with the picture that we proposed at the beginning. But now the question is, how does this dipolar interaction exactly influence the diffusion of magnons? Because in this kind of geometry, magnons propagate in a diffusive regime. So how does it work? Well, first of all, we did measure the spin diffusion length under certain field configurations. So for example, the left figure shows when the field is applied along the 80 degrees direction. Here, angle phi is defined between the field and negative y-axis in this figure. So under 80 degrees field application, the magnetic moment orientation between nickel iron and EG are roughly shown here. And now you can see that the spin diffusion length for these left propagating magnons actually is larger compared with the right propagating magnons. So now if we change the magnetic configuration by applying the field along 100 degrees, now the two layers, EG and nickel iron, their magnetic moment orientation are both slightly tilted along the positive y direction. So now we can see that the spin diffusion length is reversed. So basically the positive K give you a larger spin diffusion length, and then the negative K give you a smaller spin diffusion length. So here, the spin diffusion length is try to change the distance between the two electrodes, platinum electrodes, and then as well as the nickel iron gate width, so that we can get the transmission rate under different spacings between those two electrodes, and then that tells us the spin diffusion length. So therefore, from this, we can see that the classical diffusive picture, where you have isotropic spin diffusion, isotropic diffusion lengths for particles inside solids, no matter whether it's electrons, phonons, or photons, does not hold anymore. So here we saw an asymmetric diffusion picture for magnons due to this kind of dipolar interaction. So for one direction, the spin diffusion length can be very short, and for the other direction, the spin diffusion length can be quite long. And then this asymmetric magnon diffusion length can be controlled by tuning the equilibrium magnetic orientation. So this is what this experiment shows. So how do we explain this? Well, previously we said, actually, if you have a bilayer system, depending on your spin wave propagation direction, actually you will have two different situations. One is coupled, the two layers are coupled together. In the other case, the two layers are not talking to each other. So what exact detailed mechanism does this lead to? Well, now if you consider two oscillator system or two spin wave system, then naturally you can utilize a 2x2 matrix to describe it. The diagonal element represents the intrinsic frequency from the two layers individually. For example, omega-1 is the nickel iron frequency, the omega-2 is the EG frequency. And then the magnon-magnon interaction will enter into these two off-diagonal elements. And we know actually when you solve this kind of 2x2 matrix, because of the hybridization, because of the coupling between the two modes, it will have separate effects onto the real part and imaginary part of the eigenfrequency. The real part of eigenfrequency, of course, is just dispersion, it's just the frequency itself. And we know when two modes have degeneracy, the off-diagonal element will just simply lift up the degeneracy. You will get an anti-crossing gap. For the imaginary part, which is representing the dissipation, and we know when the two modes are degenerate with each other, actually this will lead to a average of the original damping coefficient. So as this as a crossing frequency, the originally low frequency will actually get dragged. The originally low damping coefficient will drag up, and then the originally high damping coefficient will be dragged down, so that they meet with each other. So those are the two known influences coming from magnon or oscillation hybridization. Okay, so which one plays the dominant role here? So actually we can utilize the material parameters of Ig and Pomeroy to really calculate the magnon dispersion relationship. You can see that at some low frequency, there could be some near degeneracy or degeneracy. But actually, if we just simply utilize the real part hybridization, actually, it doesn't give us too much difference between the two oppositely propagating spin waves. But now if we consider the dissipative part, the damping part, actually we see the effect is much stronger. The reason is now imagine if you have the right propagating spin wave, so those two modes are coupled, those two layers are coupled together. So the Ig damping particularly will improve or be increased quite a lot because it's coupled with this lossy Pomeroy layer. But for the other propagation direction, because the Ig and the Pomeroy do not talk to each other much, therefore the low frequency, low damping coefficient of Ig is still kept. So we believe that this is the main, the dominant mechanism that give rise to the non-reciprocal magnon diffusion. So actually, after you get this effective damping coefficient under the magnon-magnon coupling, you can utilize the Boltzmann transport theory to really calculate the spin diffusion length. So here I will not go into the details of Boltzmann transport equation. I just want to draw your attention to two scattering time. One is this spin conserving scattering time, and the other is spin non-conserving scattering time. And this non-conserving scattering time is basically related to the inverse of the damping coefficient. So just like the diffusion of electron case, the spin diffusion of magnons is spin flop time, is spin diffusion length is also proportional to the square root of those two scattering time. So now since you have some asymmetry in the non-conserving scattering time, now you can imagine correspondingly the spin diffusion length will also show some asymmetry. So that's exactly the reason why we can observe this kind of non-reciprocal magnon diffusion. So of course here we can theoretically calculate the spin diffusion length for both directions under different field configuration. So we can see that the theory can explain our measurement. Okay, so after showing this kind of non-reciprocal diffusion of magnons, we would like to argue that this can be potentially useful as a non-volatile gate tunable signal isolation device. So as shown in this measurement. So in this measurement, we particularly try to show the non-reciprocity ratio change as a function of applied field. So here we can apply a field along the y direction, either along the positive y direction or along the negative y direction to toggle between those two opposite configurations. We found that depending on the magnetic relative alignment between those two magnetic layers, we will get a non-reciprocal ratio either with a positive sign or negative sign. Here, the non-reciprocal ratio is defined as a right propagating non-local voltage minus the left propagating non-local voltage divided by their normalized by their maximum value. So here it shows that you can get this kind of non-volatile control on the non-reciprocity of this magnon transport system. So of course, if you want to further increase the non-reciprocity ratio, you can potentially utilize two materials that has even larger difference in their magnetic damping, because previously I showed that it's because of average of those two damping coefficients that leads to a asymmetry between the two oppositely propagation directions. If you have an even larger difference in the magnetic damping, you can potentially get even larger effect from this. And secondly, of course, if your two modes, if the two layers dispersion curves are very close to each other, if they are always nearly degenerate, then this effect will also get stronger instead of only crossing with each other at one single frequency. Okay, so basically this is first experiment that I would like to discuss, which is to utilize the magnetic bilayers to realize non-reciprocal magnonic diffusion, try to exploit the chiral dipolar coupling. Following this, I will talk about some topological aspects associated with this kind of chiral dipolar coupling, where we show this kind of tunable churn bands in a magnetic multilayer. This is mostly a theoretical study. So as we have already seen that by just considering two magnetic layers, whether they are coupled or not coupled with each other, we probably already get some feeling that this dipolar interaction actually plays a role that is very similar to a spin-orbit coupling for electrons. The way to see this is like this. So this is still the 2x2 matrix that I just showed. The off-diagonal element corresponds to this magnon-magnon coupling. And I said this magnon-magnon coupling is strings, actually is related to the propagation direction. Actually, mathematically, you can prove it can be finally written in this kind of format, which is k absolute value plus minus k. Therefore, for one direction, you always get 0, and for the other direction, you get a finite number. So what this does is that, well, of course, B here is a coefficient that is related to the magnetic moment orientation, the equilibrium configuration. So this dipolar, this off-diagonal element actually correlates the propagation direction of the wave vector with the polarization of the magnons, or equivalently, the equilibrium orientation of magnons. So here you couple the magnon precession polarity with wave vector, which is very similar to the electronic case. In electronic case, for spin-orbit coupling, you have the wave vector coupled with the spin orientation. So this has a very good analogy. So now we know by utilizing spin-orbit coupling, you can realize various types of topological band structures for electronic system. So now the question is, can we also construct some topological band structures utilizing this kind of dipolar coupling? So this is what we try to address here. So of course, constructing magnetic topological structures is not new. People have thinking about this since almost a decade ago, because after the discovery of electronic topological insulator, for example, like bismuth selenide, and we know there are quite a lot of interesting properties associated with those topological insulators, like those kind of Dirac cone from the surface band, the bulk gap, while the surface is actually conductive, and then the surface has this kind of spin momentum locked features. Now the question is, if you want to realize this kind of magnonic analogy of topological insulator, you also need to introduce some spin orbit-like mechanisms. DMI, as I introduced earlier, can be one of these kind of mechanism, because here you can see that this SI cross SG is already very similar to the spin orbit interaction Hamiltonian. So for example, in this case, people theoretically study this kind of complex oxide material, and then through some symmetry breaking, you can realize the topological magnetic band structures. Besides DMI, dipolar interaction has also been employed to realize topological band structures. So for example, people theoretically consider such kind of matrix system where you have an EG underlying medium, and then inside the EG, you will make some periodic arrays of iron dots. And then because of dipolar interaction between those two, you will realize also magnonic topological insulator states. In those existing studies, actually, both of them require some special crystals, some crystals with certain kind of symmetry breaking or some nanofabrication technique. So for example, this kind of nanofabrication technique is highly advanced, which is not very easy to realize. Since in our previous example, we already see that this kind of magnetic bilayer system exhibit these kind of spin orbit coupling-like features. So now the natural question is, can we simply extend this system to realize a topological magnonic band structure? So the way that we realize this is just simply repeat this bilayer structure by n times. So make a bulk multi-layer magnetic system. In this bulk multi-layer magnetic system, you have a unit cell. So you have within each unit cell, you have two different magnetic layers, and those two different magnetic layers are anti-parallelly aligned with each other. And then when you repeat it for n times, you get n unit cells, and you can talk about the intra-cell coupling as well as inter-cell coupling. So we want to make sure that each of those two neighboring layers are anti-parallelly aligned with each other. So how do you realize that? Well, of course, you can imagine you can utilize RKKY mechanism, like in the synthetic antiferromagnet, or you can just simply utilize two layers. One is a magnetic insulator, and the other is ferromagnetic metal. So for example, recently, people realized that if you simply put two layers together, ig and cobalt or ig and permalloy together, you do get anti-parallel alignment between them at equilibrium. So actually, this was first illustrated in this PRL paper, where they found that you can have this kind of anti-parallel states from the magnetization curve measurement. Actually, this was also supported by measuring their FMR frequencies. So in our own recent studies, for example, by coupling ig and permalloy together, we also found this kind of anti-parallel alignment at a low field region. And these coupling strengths actually can be quite strong, up to about, for example, 1,000 Ørsted in order to fully align those two layers together. So basically, this is to show that to realize a multi-layer magnetic heterostructure that have anti-parallel alignment between neighboring layers is theoretically possible. So now let's try to analyze this multi-layer system by looking into its Hamiltonian. As we discussed earlier, since this is built from two different magnetic films, so you can, after you do the Fourier transform along the z-axis, because along the z-axis is periodic, so you can again get this 2x2 matrix. And then the diagonal element comes from the intrinsic frequencies of the two films. And then the off-diagonal element describes the intra-cell or inter-cell coupling. As you can tell that actually this 2x2 matrix is very similar like the SSH model where people utilize to study electronic topological insulators. So if you look at the diagonal element, omega-1 and omega-2, they are the intrinsic frequency from ig and permalloy, for example. And then within each of their expression, you will have this exchange term. So this is the exchange within the same layer. And then there is also the Zeeman term. For the Zeeman term, is proportional to the net field that each layer experiences. So it includes the exchange field, interfacial exchange field from the neighboring layer, as well as applied field. Because the two layers are anti-parallel with each other, but you can only apply field along one fixed direction. So for omega-1, you have minus sign, and for omega-2, you have plus sign. Okay, so now you can imagine, since you have two different magnetic layers, and their exchange stiffness will be different. A1 and A2 are not the same. So you can imagine, you can construct such kind of bending inversion situation. If we choose A1 to be bigger than A2, for example, permalloy is known to have a larger exchange stiffness compared with E. Then, and also if you choose the external field appropriately, you will have this kind of bending inversion situation, where at low wave vector, at the center of the band zone, the ig frequency is higher than permalloy frequency. But as you increase the K, now the exchange terms dominate. So the permalloy frequency now becomes larger than ig frequency. So this is the band inversion situation that is usually required for realizing a topological insulator system. But of course, you can also realize this kind of normal band configuration by changing the applied field. In this case, there is no band inversion. Okay, so this is about the diagonal element where you can utilize the external field to tune the band inversion configuration. Next, let's open up the band gap by utilizing the off-diagonal element, the intracell coupling and the intercell coupling. As I explained earlier, the intracell coupling comes from the coupling within each unit cell. So for example, if we consider the right propagating spin wave, then this is the same situation as we discussed earlier. The two layers within the same unit cell will couple together, but the two layers across a boundary of unit cell does not couple to each other because there is no dipolar field at the boundary. But now if you flip the spin wave propagation direction, you will see that the intercell coupling becomes finite, while the intracell coupling becomes 0. So delta S and delta D is always 1 equal to 0 and 1 equal to finite because of the dipolar interactions property. So by utilizing this delta S and delta D, the intercell coupling of diagonal element, we can now open up the gap and then get the topological state. So actually you can solve this 2x2 matrix and then get the eigenstate and also get the Berry curvature. And by doing the integration over the full grand zone, you will be able to calculate the train number. It's either plus or minus 1 or 0. And for the 0, of course, it's normal case. And then for the 1 or minus 1, it's topological non-trivial case. So if you look at the band structure, they look like this. The black lines represent the bulk states, and then these red and black curves represent the surface states that are geometrically located at the top and bottom of the multi-layers. So this left figure, it has a certain field. It's relatively high field. So this corresponds to the band inversion case. After we open up the band gap, we found that there is a Chiral cone due to the surface states formation. And then on the right side, there is no band gap. But for the normal band case, where the field is relatively lower, we found that the train number is 0, and then there is no Chiral cone in either side of this brane zone. So here, because you break the time reversal symmetry as well as the inversion symmetry, so this is a system with very low symmetries. So that's the reason why actually the Chiral cone actually show up in one side of the brane zone instead of at some high symmetry point. So it does not show up at the gamma point. It shows up as the one side of the brane zone, which is a quite interesting feature and quite unique compared with all the other topological systems that people discussed so far. So this is a bulk band where you can calculate the train number, the topological invariance. So actually you can also understand the surface mode generation by utilizing this kind of coupled wire construction model, which is heavily used for understanding, for example, quantum Hall states. But here I would like to skip this part. But the bottom line is that you can intuitively understand how there can be a generation of a pair of surface spin wave mode or surface spin current that goes in a chiral way, no matter whether you have a total even number of individual layers or total odd number of individual layers. So actually, in the previous case, we only constrain the magnitude to move along the XZ plane, and we can also make it more general to also allow it to propagate along the y-axis, and also we can include all real interactions, including the dipolar interaction within each layer, as well as exchange interaction interface. We found that the conclusion remains qualitatively the same. So you still get this kind of band inversion case. You still get this crossing from the surface band, surface states, and then for the normal case, you still get this trivial band structure. So of course, those are just analytical results. We can also do micromagnetic simulation to further verify this. So here we consider a simplest structure where we only have a bilayer, just one elliptic film and one permaloid film. And then we can utilize some pulse excitation, which has a sync waveform so that we can get a broadband excitation. And then after that, we do Fourier transform. We found that this dispersion relationship actually is very consistent with our analytical results, where on one side, you will get a crossing, get a Chiral cone, and on the other side, you will get just a band opening without a surface states. So now that means if you excite the spin wave in the middle, you're particularly this frequency omega 0, which crosses with the Dirac point, which while being located in the gap of the two curves, you'll find that actually it only propagates along one direction, but not along the other. So this is, again, consistent with our analytical understanding. So finally, is a summary. So today I'm talking about two related systems. One is about diffusive non-reciprocal transmission of spin-Hall effect excited magnons in a bilayer film, which is nickel iron and E. So basically, we found that you can realize some tunable non-reciprocity by changing the magnetic moment orientation. So the main mechanism that accounts for this non-reciprocity is coming from the hybridization of the two magnon modes, while the cover dipolar coupling, which changes the relaxation rate along two directions asymmetrically, and also lead to asymmetric magnon diffusion lengths. So we also construct such kind of topological magnonic system by making a multi-layer anti-parallel aligned magnetic system. We found that you can calculate the topological invariance, the Chern number of such a system. By using the external field, you can toggle between the topological trivial and non-trivial situation, and then get some non-trivial surface states. Hopefully, those topological protected surface states can provide robust non-coherence and unidirectional surface spin current that can be useful for some signal isolation device. So those results are summarized in those two papers. Thank you for your attention.
Thank you very, very much, Luqiao. That was a very nice talk on the breadth of ideas that you bring together. So now we're open for questions. Please raise your hand. Hang on. Let's see. Let's have Bart join us. Okay. So he and then also has. So once they join, so Bart, go ahead and unmute yourself and ask your question, please.
You can hear me now?
Yeah, we can hear you.
A very beautiful talk. Thank you very much. But my question is, how thick was the YIG layer in your experiments?
So let me see if I write it somewhere. I don't remember. Well, if it's not written in these slides, my memory is about on the order of 50 nanometers.
On the order 50?
50
nanometer. And can I ask one more question?
You can ask as many as you like, Bart.
Good. Okay. Can you show me the data again a little bit further on, I think, from this one? Yeah, here. I was a bit surprised if you look at the right panel, there is quite a jump at 90 degrees.
Yes.
And at 90 degrees, the magnet. So why is there this jump? Because there is this nickel iron has the, let's say, has a shape and isotropy by itself, because the magnetization likes to align along the length of the strip. So if you try to pull it out of that direction, you would have a slow. Well, I mean, it would slowly saturate the magnetization in that direction. But here there's a jump.
Yes, that's exactly. Yes. So basically, this jump comes from the reversal of the nickel iron layer from slightly parallel with the positive y direction to slightly positive parallel with the negative y direction. Yes, those sharp edges reflect this reversal of permaloid. Yes.
I'm still confused, because 90 degrees means that the field is perpendicular to the strips, right?
Yes, yes. So if it's slightly, for example, 80 degrees, then it favors this minus y direction. If it's 100 degrees, it favors the positive y direction. So that's the reason why it switches at about around 90
Oh,
degrees.
because there is also a component along the lengths. Okay, I understand. Thank you. Yeah.
Yeah, thank you. Nice question.
Sasha, can you unmute yourself? You need to unmute yourself. Hang on a second.
Thank you very much for my connection. Thank you very much for very interesting talk. And it is interesting for me also if you take into account or try to estimate influence of metal surface boundary conditions in this non-reciprocity, because it's known that metal cover changes the existence band of spin waves, and also for that spin waves which propagate where the maximum of, for example, surface spin waves, where the maximum of dynamic magnetization closer to the metallized surface, and significantly increase the group velocity of these. Tried to estimate this from such point of view as influence of metallic boundary conditions. Not only magnetic change interactions. Here it's only the question because it's clear that you have very thin layers, and very thin layers where the thickness is smaller than the skin length. For electromagnetic wave at the given frequency, its metallic influence should not be very pronounced, but still maybe it is plays some role.
Yeah, that's a good question. So I guess to be more rigorously characterize the Magnon mode, so basically to impose those kind of exchange, maybe dominated boundary condition, so that they better describe this bilayer system. So I think that's totally something that I guess one should do. So in our study so far, we just utilize, the picture such that, for example, the EEG, it does not have any detailed features along the z-axis. So there is no additional mode along the z-axis. So, well, of course, we can include those the higher order perpendicular standing spin wave mode, PSSW mode, due to the interfacial exchange interaction. So actually, we did some calculation along that line. After we include those PSSW mode, actually it does not quantitatively change the final conclusion.
It is, as a comment, it's not only the PSS perpendicular standing modes, it's also for Damon-Eschbach mode, and principally it is such that it's not exchange boundary conditions, completely electrodynamic boundary conditions. But if you are speaking about the dipolar interactions, it looks for me that waves which participate and contribute to the observed effects are rather long wavelengths spin waves, because dipolar interactions still visible in comparison with the exchange one. And that is why, and contributes a lot to this non-reciprocity and others, and maybe that is why some metallic boundary conditions also contribute.
Yeah, so, well, of course, so here we previously talked about the exchange interaction use some boundary condition. If we also impose this dipolar interaction imposed boundary condition, so I guess to some extent it might be equivalent to the description I try to give here, because here I also try to utilize this kind of dipolar interaction to describe their interactions. But of course, here I do not consider the finite width effect. There I probably are considering the extra mechanism coming from the edge poles of the finite width of the nanowire. Maybe that's what you are trying to emphasize there.
Yeah. It would be very interesting to understand it, because you see that permalloy is metal and simultaneously magnetic metal. Yeah?
Yes.
But it would be interesting to look if it will be only metal, for example.
Only metal.
Only metal, not magnetic, but only metal. Or if the second layer will be only magnetic,
I think you are talking
metallic.
about the effect coming from for example, eddy current. The screening of the electromagnetic wave.
It's partially screening, but for Damon-Eschbach mode, the group velocity, for example, in thick film, will increase if by application of metal layer on the top, maybe 5-6 times, and it can contribute to the diffusion length a lot. Change in the velocity, in the group velocity of propagation.
Yeah. So I agree. I think since as we throw more and more factors into it, it becomes more and more difficult to analyze. So I guess in the end, probably the way to go is just to utilize micromagnetic simulation. So actually, we did some micromagnetic simulation about this system, and we get these quantitatively consistent results here. But of course, in that micromagnetic simulation, I don't think we consider the eddy current. So there are probably still factors not included.
Yeah. Okay, thank you very much for your answers.
Thank you. This is very
for your talk.
suggestion. Thanks.
Okay. I don't see more questions on the audience. So with that, I'd like to maybe stop here the streaming. Now we ended up. And thank everybody for attending. It was about,